This is an example that has been presented in class, and this is a slightly more complicated example of using equivalent resistances. The ultimate goal for this problem and this circuit is to determine the power that is dissipated by resistor R6, which is this 200 ohm resistor here. Now we have a slight complication with this because in this problem we now have a dependent voltage supply. And this dependent voltage supply, which is indicated by this diamond shape right here, depends upon the amount of current that's flowing through resistor R4. What this circuit is going to do, or what this element does, is it's going to be connected to this current flow, and depending upon how much current flows through resistor R4, it's going to provide a voltage that is proportional to that current. Here, the constant of proportionality is 1000, so that means for every 1 amp of current that flows through R4, we will get 1000 volts out of this voltage supply. To analyze this circuit, basically, these are two separate circuits that are connected only by this one ground or reference wire. So to analyze this, in order to determine the power that's dissipated by resistor 6, first of all we need to know what the potential is, or the voltage is, that's developed by this dependent supply. Before we can figure out the voltage that's developed by this dependent supply, we need to know how much current is flowing through resistor R4. So what we can do is we can analyze the left-hand side of the circuit first to determine the current through resistor 4, and then go on to analyze the right-hand side of the circuit to ultimately meet our goal of determining the power that's dissipated by resistor 6. Alright, so we're going to work to find this controlling current through resistor R4 using the concept of equivalent resistances. So I'm going to take the left-hand side of the circuit and begin trying to reduce that circuit into a single equivalent resistance. So up here we see that resistor 2 and resistor 4 will have the same amount of current flowing through them, but they may have a different potential developed across them. Since they see the same amount of current, those two resistors are in series with each other, so I can create an equivalent series resistance for the two of them, which I will call R24. From our series addition, we know that R24 is equal to the addition of resistance of element 2 plus the resistance of element R4, which in this case is 6.4 ohms plus 1 ohm gives us 7.4 ohms. If I redraw this circuit, I also see now that R24 is in parallel with resistor R3, which is 2.2. So again, I'm going to reduce my circuit by creating an equivalent resistance which combines R24 with R3 to give me R2, 3, 4 equivalent. And I determine that equivalent resistance by using my inverse addition formula for parallel resistors. So R2, 3, and 4 is equal to the inverse of R3 plus 1 over R24, which is the same thing as, given the values that we have, 2.2, 1 over 2.2 plus 1 over 7.4. And when I perform that operation, I wind up with 1.6958, there's some more digits there, ohms. What I'm going to do, what I always practice doing, is carrying many more digits than we need so that at the end, when we round our results, we'll be confident that our results are correct throughout the entire calculation. Okay, so now I know that this equivalent resistance is 1.6958 ohms. And I know that resistor R1 up here has a resistance of 8 ohms. Again, we see that both of these resistors will see the same amount of current through them, so they are in series with each other. My next step now since I'm not really interested in the total potential developed across this 0.2 amp current supply, is that I do not need to combine resistor 1 in series with resistor 2, 3, and 4, which we calculated to have an equivalent resistance of 1.6958. Ultimately, I want to know how much current is flowing through the resistors that comprise this equivalent resistance. To do that, I'm going to need to determine the potential that's developed across this equivalent resistance. So I can use Ohm's law, because I know that 0.2 amps must flow through both R1 as well as this R2, 3, 4 equivalent. Using Ohm's law, I know that the voltage developed across that resistor is going to be the current flow through that resistor multiplied by its resistance. That gives me 0.2 amps multiplied by 1.6958 ohms of equivalent resistance. That results in something like this, 0.33917 volts. Remember that I'm going to continue to carry more digits than I really need so that in the end we will wind up with accurate results. Now I'm going to expand my circuit again. So right here I've calculated that the potential difference with respect to this 0 volt reference right here is 0.33917 volts. I'm going to expand my circuit again into R3, which was 2.2 ohms, and the equivalent series resistance of R2 and 4, which we calculated earlier to be 7.4 ohms. Both of these resistors, with respect to our 0 volt reference, have 0.33917 volts of potential across them. That's right here as well as right here, and really anywhere along that wire. So I also know that the amount of current that enters this node, which is 0.2 amps, must be balanced by the current leaving both of the nodes. Ultimately, I'm interested in the current that flows through the combination of resistors 2 and 4. So I can calculate that using Ohm's law yet again. Ohm's law tells us that the current that is going to be flowing through resistor 2, 4 equivalent is going to be equal to the potential that's developed across that resistor, which is 0.339 volts, divided by the resistance of that element. So if I plug those values in, I wind up with a current through that equivalent resistance of 0.04583 amps. Now I'm going to expand the left-hand portion of the circuit yet again back into its original form. Remember that what we're interested in is the amount of current that's flowing through resistor R4. We've calculated that the amount of current that flows through the equivalent resistance of R2 and 4 is 0.458 amps. Since R2 and R4 are in series, they both see the same amount of current. Therefore, we don't have to do any more work to determine the amount of current that flows through resistor 4. We've already calculated that. So now we know that the controlling current for the dependent voltage supply is equal to 0.0458 amps. From our original circuit here, on the right-hand side, we know that the voltage potential that's developed by this dependent voltage supply is going to be 1,000 times the current that passes through resistor R4. Since we now know the current, we now know how much potential is developed by this dependent voltage supply. So we multiply that current by 1,000, And that will tell us the potential that's developed on the right-hand side of the circuit will be 45.83 volts. I did not include that there. All right, now that we know that the voltage supply right here provides now that we know that the voltage supply here provides 45.8 volts to the right-hand side of the circuit, we can use our equivalent resistance concepts again to determine ultimately how much power is dissipated by resistor R6. So now I'm going to work with the right-hand side of the circuit. We know that this voltage supply now provides 45.83 volts of potential across R5, which is 160 ohms, R6, which is 200 ohms, and R7, which is 270 ohms. R6 and R7 will both see the same potential, so they are in parallel with each other. So I will combine those in parallel to come up with an equivalent resistance for them. So the equivalent resistance of R6 and 7 combined is going to be 1 over R6 plus 1 over R7, and I'm going to take the inverse of that. And that will give me an equivalent resistance of 114.89 ohms. So now I've reduced my circuit to look like this, where I have my 160 ohms in parallel with the equivalent R6-7 of 114.89 ohms. Since these are in series with each other, I know that I can add them to come up with the equivalent resistance. So the equivalent resistance of R5, 6, 7 is going to be 160 ohms plus the equivalent resistance of R6, 7, which I just calculated, 114.89, which gives me a total equivalent resistance of 274.89 ohms. Oops, 45.83 volts is now being supplied across an equivalent resistance of 274.89 ohms. Now, using Ohm's law, I can determine how much current this voltage supply must be providing to the circuit. The current through the circuit is going to be the potential across the resistive element divided by the resistance of the circuit. So that is 45.83 volts divided by 274.89 ohms. And I find that the voltage supply must be providing a current to the entire circuit of 0.1667 amps. With that in hand, now I'm going to expand my circuit yet again. Into my R6-7 equivalent. And I can determine the potential that's developed across R6-7 equivalent, since I know the current flow through it. So the voltage that's developed across R6-7 is going to be the current flow through the resistor multiplied by the resistance. 0.1667 amps multiplied by 114.89 ohms of equivalent resistance. Gives me a potential difference across that equivalent resistance of 19.15 volts. Okay, so that means right here, with respect to some reference, it's going to be 19.15 19.15 volts of potential developed. We're almost there. Again, I'm going to expand my circuit yet again to include R6, which is the 200 ohm resistance, and R7, which is the 270 ohm of resistance. And I know that across both of these, right here, with respect to a zero voltage reference, right here, I have 19.15 volts. Right, so they both see the same potential across them, but they're going to have different amounts of current flow through each of them. I'm interested in the power dissipated by R6, so what I need to do is compute how much current flows through resistor R6. Again, we'll invoke Ohm's law, and we can determine the current through R6 by dividing the potential across R6 by its resistance, which results in 0.0958 amps. Finally, I can calculate the power that's dissipated by resistor 6 by multiplying the voltage developed across R6 by the current through resistor R6. That's going to be 19.15 volts multiplied by what we just calculated, 0.095 amps, which gives us a total power dissipation of 1.83 watts. Alternatively, instead of going through the process of calculating the amount of current that flows through resistor R6 and using my power is equal to voltage times current formula, since I know the potential developed across R6, I could also use the alternate formula for calculating power across R6, which is the potential that's developed across R6 squared divided by the resistance of R6. Both of these methods would give you the same result.